Section 3.2 is on nonlinear models. 3.1 was on linear models. And it starts out saying in chapter 1, one of the applications of differential equations discussed was population growth. In ideal conditions, the growth of a population is directly proportional to the current population. So, and growth, when they say growth of a population, that corresponds to rate of change, which is represented by a derivative. So the corresponding differential equation is, the derivative is, and remember, proportional to means constant multiple of, so it's equal to k, where k is some constant, times the current population, p. And for growth, then k would be a positive constant, often referred to as the relative growth rate. Or we could get an equivalent equation by multiplying both sides by 1 over p. In the mid-1800s, the Belgian mathematician P.F. Verhulst came up with the logistic equation to help predict the human population in various countries. Verhulst recognized that humans do not live in ideal conditions, but that the rate of population growth is affected by both birth and death rates. Using the simple equation above, he assumed that the rate of growth, so that the left-hand side of that last equation, is equal to the average birth rate minus the average death rate. He used the letter A to represent the average birth rate, which he assumed to be constant for a country, and assumed that the death rate was proportional to the current population. So the higher the population, the more likely it is for a disease to spread. So that's why it depended on the current population. So here B is the constant of proportionality for the death rate. And now they're just solving for the derivative again. So they're multiplying both sides by P. So there is the logistic equation. And it says, determine the general solution of this differential equation. Assume the initial population is P naught and that P naught is not equal to A over B. And the reason they do that is because this second factor is equal to 0. So if we add BP to both sides, we would get P equals A over B. So that would be when the population is in equilibrium already. So we're assuming that when it starts out, the population is not in equilibrium. And we're told here to get the arbitrary constant after we integrate in terms of P naught. Okay, so this is a separable differential equation. So I am going to multiply both sides by the reciprocal of the right-hand side and by dt. So I'm going to do dt over p times a minus pb. Okay, so on the left, the dt's cancel, and I'm left with 1 over p times a minus pb dp, because the dt's cancel there. And then on the right, the p times a minus pb's cancel, and all we're left with is dt. If you want, you can put a 1 there. So now I've separated the variables, which means I'm ready to integrate on both sides. But on the left, I'm going to need to use partial fractions to integrate. And so remember, for partial fractions, in the decomposition, we have as many fractions as we have factors in the original denominator, and we have 2 factors. One of them is p, and one of them is a minus bp. I'll just use capital A and capital B as my constants in the numerator. And then I like to multiply both sides by the LCD. So on the left, all I'm left with is 1. On the right, the A will be multiplied, the P's will cancel, and I'll be left with A minus BP. And for B, that factor will cancel, and it will just be multiplied by P. And then I'm free to plug in any value of capital P that I want. It's best to plug in values that make those denominators equal to 0. And the first denominator is 0 just when P is 0. So I would get 1 equals capital A times little a. So capital A equals 1 over little a. And then I would substitute in P equals A over B. And I would get 1 equals, now the first set of parentheses is 0, and I would just have B times little a over little b multiplied by the reciprocal. So capital B is equal to little b over a. So now I can rewrite the left-hand side as the integral of those two fractions. So I'll write it here. So I have 1 over little a over p plus, and then b, little b over little a divided by a minus little bp. That is all d capital P equals the integral of dt, and if it helps, you can think of having a 1 there. So on the left-hand side, our answers are going, or the antiderivative is going to involve natural log. I'll pull the 1 over a out in front. Natural log of p, I don't need absolute value because I would never have a negative population. Plus, and then put the b over a out in front. Okay, so I know I'm going to have the natural log of a minus bp, but I am going to need something else. So let's think about what we need there. If I take the derivative of just ln of a minus bp, I would get 1 over a minus bp and then times the derivative of what's inside parentheses, which would be negative b. And since I don't have that, I need to multiply by the reciprocal. So times 1 over negative b. And then on the other side, the antiderivative of 1 is t plus some constant. Okay, so on the left, the b's cancel. And then both terms have 1 over a, so I can factor that out. And I'm left with ln of p minus ln of a minus bp. Equals t plus c. I'm going to eventually want to exponentiate. So I think I'm going to multiply both sides by a here to clear the fraction on the left. So I would just have natural log of p minus natural log of a minus bp, but I'm going to apply properties of logarithms and write it as the natural log of p over a minus bp equals at plus, okay, c times a, well, c is a constant, a is some constant. When we multiply them together, we just get some arbitrary constant. I'm just going to call it c again. Now I will do e to both sides. And so on the left, the e and the natural log kind of cancel each other out, and I get p over a minus bp. And on the right, I'm applying properties of exponents to give me e to the at times e to the c. But e is a constant, c is a constant. So together, they just make a constant that I'm going to call k. And that's the constant that we want to get in terms of the initial population. So it tells me when t equals 0, p equals what they're calling p naught, the initial population. I'll just, I think, plug in t equals 0 right now. And I'll plug in p naught for p. So p naught over a minus b p naught equals k. And then I'd have e to the 0, which is just 1. So there is my k. Okay, so I'm just going to make a note of that. But instead of plugging that in to my solution, I think I'm just going to leave the k in there and then just make a note at the end. Okay, here's my k. What I really want to do is solve for p. I want to get the population as a function of time, t. So I have 2 p's in that expression just above the equation that I boxed in. I want to just have 1 p and then everything else on the other. So I'll think of that k e to the at as being over 1 and cross multiply. So I do p times 1, which is just p, equals k e to the at times that denominator. And then distribute. And then add the term with p to both sides. And then when I do that, both terms will have a p in common, so I'll factor it out. And I'll get 1 plus bk e to the at equals k a e to the at. And then divide both sides by what's in parentheses. There are lots of ways to write this. I personally think the nicest way to write it is to divide everything by e to the at, but the book might divide by a. I think I'll just leave it like that for now and see how we can apply stuff to the next problem. I think when I originally wrote the notes, I maybe divided everything by k e to the at. I'm just going to look at my old notes here. Nope, I left the k there. I just divided everything by e to the at, which is the same as multiplying by e to the negative at. You can do it that way, and you see that I get my, I called it m there, but that's my k in this problem, p naught over a minus b p naught, which is exactly what I have here. So I just have a different letter. Okay, so let's see how we can use that in problem 2. So it says the number of people in a community who are exposed to a particular advertisement is governed by the logistic equation. Initially, n of 0 equals 500. So that's like our n naught or p naught. So I'm just going to rewrite the equation we had. So p equals k a e to the at over 1 plus b k e to the at. Where k was equal to p naught over a minus b times p naught. Okay, it's just we're using n's instead of p's in this problem. So 500, that's our n naught. So I'll plug that into the equation for k. We still don't know a and b though. So I have 500 over A minus B times 500, or 500B. The one thing, when I had it in my notes the other way, the one thing that's nice about dividing every term by e to the AT or multiplying by e to the negative AT is it's pretty easy to see what happens as t goes to infinity then, because the MA and the MB, they don't even have a t in it. And when we divide 1 by e to the AT, we just get 1 over e to the AT or e to the negative AT. And A and B were both positive constants. So as t goes to infinity, the e to the negative AT goes to 0. So I would just get MA over MB, and you can cancel the M, so you just get A over B. So in these problems, the limiting population, or as t goes to infinity, the population goes to A over B. I see I have a note here to write small. I have a really hard time writing small when I'm doing things on the computer. I can write small when I'm doing it on paper, not so much when I'm doing it on the computer. So they tell us the limiting number of people, what that means is in the long run. So the limiting number of people who will see the advertisement is 50,000. That is this right here. So A over B is 50,000. As time goes on, we reach the limiting number. So A over B equals 50,000, which means A equals 50,000 times B. And we can substitute that in for that A. It will help us a little bit. So in place of A, I'll put 50,000 B minus 500 B. Well, 50,000 minus 500 is going to be 49,500. And 500 will go into both of those. And 500 goes into 49,599 times. So K is 1 over 99B. We still don't know what B is yet. Okay, so I've used the 500. I have not used the n of 1 equals 1,000. I've used the 50,000. So I'm going to rewrite I'm going to modify this equation using the information I know so far, but going to replace the P with N. So I would have N equals, so it was K times A. So I'm going to use what I've just found for K, 1 over 99B. A is 50,000 B. E to the AT, and A is 50,000 B times T. So there's my K, A, E to the K, E to the AT, and then in the denominator I have 1 plus B times K, and K is 1 over 99B. E to the AT. And A is 50,000 B times T. So let's just simplify that a little bit. So I see those B's cancel and these B's cancel. And then, okay, I'll just write it as, so in the numerator, I'll have 50,000 over 99. E to the 50,000 BT all over 1 plus 1 over 99 e to the 50,000 b times t. And then I don't like fractions within a fraction, so I am going to multiply numerator and denominator by 99. So in the numerator, the 99s would cancel, and I just get 50,000 e to the 50,000 bt. And in the denominator, I have to distribute the 99, so I get 99 plus e to the 50,000 bt. Now I will use the fact that n of 1, I think, is 1,000, because I still have to figure out what b is, right? T should be part of my formula. T is time, and that's changing, but I should be able to figure out what b is. So I'll plug 1,000 in for n and 1 in for t. So that would just be 50,000 b. This is where it is nice to multiply numerator and denominator by e to the negative 50,000 b, because then we'll just have b in one spot. It's a lot easier to solve for b if it's only in one spot as opposed to two. So in the numerator, then I just have 50,000 Daff. And then I'd have 99e to the negative 50,000 b plus plus 1. I would probably multiply both sides by 1 over 1,000. So then I would just get 1 equals, so on the right, the 1,000 cancels 3 of those zeros, so I just get 50 over that. I'd multiply both sides by the denominator, so I would just get the denominator equals 50, and then I'd subtract 1 from both sides. I would divide both sides by 99 and then take the natural log. So on the left, the 99s cancel, and I have natural log of e to a power, so I just get that power. And then I'll just leave that for now, natural log of 49 over 99. And then divide both sides by negative 50,000. Actually, I don't know that I need to do that on my calculator now that I think about it, because when I look at this formula right here, it has 50,000 times B. So when I multiply by that B and it's got a 50,000 in the denominator, the 50,000s are going to cancel. So actually, I'm going to get rid of that and just multiply both sides by -1. Right? And then say what that is approximately. So then I can just substitute in for the 50,000 B instead of solving just for B and multiplying by 50,000. And I get about 0.7033. So my N is given by 50,000 E and then the 50,000 B is going to be replaced by 0.7033, and that would be times T. All over 99 plus E to the same power. And that's fine. It's fine to leave it like this. If you look at the completed notes that I posted, I just multiplied numerator and denominator by E to that negative power. So just the 50,000 is in the numerator and then 99 E to the negative 0.7033T plus 1. Okay. And I guess I only did 0.703, but similar. Okay, and then now for chemical reactions, so it says on pages 96 to 97, depending on what edition you have, if you have the book, it discusses differential equations as they relate to chemical reactions. The setup is very similar to the logistic equation. We'll use separation of variables followed by partial fractions to integrate. And I say you should read through the example in the book, but I'm going to talk about the system of equations on page 99. So I just, we're not going to be worrying about reaction order, but this is just how the rate of a reaction. So it tells you to what extent the concentration of a species or one of the elements affects the rate of the reaction, as well as which species or element affects the rate, or compound affects the rate the most. We're not going to worry about that though. Okay, so here it's a second order chemical reaction because we have two compounds here, or A and B, either compounds, chemicals, elements, whatever. And they're reacting to form compound C. It says the resulting reaction between the two chemicals is such that for each gram of A, 4 grams of B is used. So I don't know if A and B are elements or compounds, but we'll just say A and B are used in the ratio 1 to 4. So that means, oops, A and B. So that means for each gram of C formed, one-fifth of a gram like kind of came from A, and 4/5 of that gram came from B. So just think there, when you look at that ratio 1 to 4, that's a total of 5 parts. 1 of the 5 was A, 4 of the 5 were B. So what they say in our book and kind of what they say here as well is that the rate of reaction is proportional to the amounts of A and B remaining. So proportional to means constant multiple of, and then it would be the total amount of A, which I didn't say right in this first paragraph, it's actually on the next page. So it says initially there are 50 grams of A and 32 grams of B. So what we're starting out with is 50 grams of A, but then for every gram of C formed, we're losing 1/5 of a gram of A. So we have 50 grams of A minus 1/5 times the number of grams of C. And then B, we started out with 32, but we're losing 4/5 for every gram of C formed. We really don't want to deal with fractions when we're doing the integration and partial fractions. So what we'll do is first factor out a 1/5 from each of those sets of parentheses and just kind of absorb the 1/5 into the constant. So I'm going to factor out a 1/5 in the first set and in the second set. And then, like I said, they just kind of get absorbed into that K. So if I divide 50 by 1/5, that's the same as multiplying by 5. So we have 250 minus X. And then 32, if I divide it by 1/5, that's the same as multiplying by 5. That's 160, but then I still have minus 4X. And I don't want a coefficient of X at all. So I am also going to factor out a 4 from here and just let the K absorb that as well. So that's just going to kind of get taken into that K. And so if I factor out a 4, I'll be left with 40 minus X. And then what I'm going to do is multiply both sides by dt and divide both sides by those sets of 2 parentheses. So I'll have 1 over 250 minus X times 40 minus X dx equals K dt. And again, I write bigger on the computer than I do on my paper, so I'm at the bottom of the page, but I'm going to keep going until I get to this line is where the next video picks up. I have already the end of this problem in there, but I'll get to that point and then I'll let you switch to the other video. Okay, so I just mentioned that we're going to have to do partial fractions with this. Because I've separated the variables, I'm ready to integrate on both sides. The right-hand side is fine. It's going to be kt plus c. It's the left-hand side where we have to do partial fractions. So I would have 1 over that product equals 2 factors means 2 fractions. Each factor is a denominator. I'll just use A and B, even though we're calling the reactants A and B. You can use whatever letters you want. And then I multiply by the LCD to clear fractions. So I would get 1 equals A times 40 minus X plus B times 250 minus X. And then I would first plug in X equals 40. So I get 1 equals B times 250 minus 40 is 210. So b equals 1 over 210. And then I would plug in x equals 250. And I would get 1 equals a, and then 40 minus 250 is negative 210. So a is negative 1 over 210. Okay, I've already done the factoring out, so I'll just continue right here. So pick up with, so now I'm going to rewrite the left-hand side as, so the a was negative 1 over 210, and that was, the denominator was 250 minus x. Plus b, it was positive 1 over 210, and that was 40 minus x dx. And then it was just k dt. So for each of the fractions on the left, we just pull the numerator out in front. And then it's natural log of the denominator. And we don't have to worry about absolute values. I'll explain why here. So remember, there were 32 grams of B and 50 grams of A. So could we use all 50 grams of A? Well, remember, they're in the ratio 1 to 4. So if I use 50 grams of A, I have to use 4 times that of B, which would be 200 grams. I don't have nearly enough. So then I have to focus on B. How much B do we have available? 32 grams. And we use 1/4 of that amount for A. So I'd use 8 grams of A. So altogether, 8 plus 32. So we're only going to be able to make 40 grams of C when we're all done. So the biggest X will be, is 40. So 250 minus 40, that's positive. We don't have to worry about it being negative, so I don't need absolute value. Plus 1 over 210. Oh, I'm not done with that. Sorry. If I take the derivative of just natural log of 250 minus x, I do get 1 over 250 minus x, but then by the chain rule, I also have to multiply by the derivative of what's inside, which is a negative 1. So, oops, I need to multiply that by a negative. Man, that should be 210. Okay, so now if I take the derivative of this expression, I get what I have right above it, right? The 1 over 210 would stay out in front, and then I get 1 over what's in parentheses times negative 1, which would give me the negative 1 over 210. Okay, now similarly for the second term, I would get natural log of 40 minus x, and the biggest x could be is 40, so that will never be negative. But then if I take the derivative of that, I'd get a negative. So I need to put a negative there. And then on the right, I get kt plus a constant. And I think that's where the next video picks up. Let me check. So 1 over 210, yep, minus, yep, okay. So I'm gonna stop this problem there because the rest of it is in the other problem. And this problem, when I say solve this using Maple, when this class is not forced to be online like we are right now, I would have you do software projects, but it's too hard to make sure everybody can get Maple right now. So you can just ignore this problem. We're not going to deal with that. And I think that was the end of those notes. All right.